Hello. Okay. So if we think about it, I didn't get a temperature right. Let's look at this graph. So a fraction of molecules will have enough energy. So just to say E naught is the threshold to get to the gas state, right? So at a certain temperature, only a fraction of those molecules will have enough energy to get to the gas phase, right? But as we increase the temperature, you see the curve decreases and gets more broad, so the distribution is going to increase even more. So as we go higher temperatures, you're going to increase the fraction of molecules that have enough energy to get to the gas state until eventually you reach the boiling point where all the molecules now have reached this are past the threshold and have enough energy to go to the gas phase. And that's why when you see things boil, they always you always see more bubbling occurring, and that's because every molecule now has enough energy to go to the vapor state or gas phase. Okay. So just remember this. It's very similar to the energy distribution curve we saw for kinetic energy for gases, right? As you increase the temperature, gases will have more kinetic energy, so it'll flatten out the curve, okay? Okay. So eventually, at a certain temperature, a fraction of the molecules will form vapor, and then then some of those molecules in the gas phase will collide with the surface of the liquid, and then go back to being a liquid because they're attracted to the liquid molecules in the liquid. So that's called condensation. Okay, so eventually you collide. Molecules collide, transfer energy, loses the kinetic energy to go back into the vapor phase and stay in go back to the liquid state. Okay, so this will lead to a steady state. So a steady state is basically a state of equilibrium where two processes are happening at equal rates. Now, this doesn't mean the molecules on both sides of the processes are equal. It just means the rate of forming molecules in both states are equal. Just like you say, the rate of rainfall equals the rate of evaporation. Sort of like that. It doesn't mean that both sides are equal. Just the rate of those processes are equal. Okay, so we'll learn more about that in Chem 401 when you learn about equilibrium in chemistry. Okay. All right. So this formed the result of this process. You form an equilibrium vapor pressure. So the vapor pressure at a certain temperature will always be constant because eventually it equilibrates where these two rates are equal, and then that's the vapor pressure, and that's why, as we saw in the chapter 5, the vapor pressure of a gas is temperature dependent. Okay. All right. So here is that kind of what I just said, detailed in the graph here. Evaporation, and then condensation. Eventually things will evaporate, and then eventually those two rates will equilibrate until they're equal at a certain time. And that's the vapor pressure. Okay? So that's pretty much all you have to know about kind of like the equilibration between evaporation and condensation for vapor pressure. Okay. Now, this is only true if you have a closed system. If a liquid is in an open container or reaction vessel like a beaker, most of the molecules that enter the vapor phase won't collide with the surface of the liquid, and that's because they'll just fly out into the atmosphere and just go do its own business and won't return to the liquid phase. So equilibrium will never be established, so you're always going to have a continuous process where it's always evaporating until no liquid is left, and then that's the end of that. Okay, so that's why when you leave a liquid in like a container, water, if it's not closed, all the water will eventually evaporate, but it's very slow. But if you have a very volatile liquid such as methanol or diethyl ether, eventually, if you leave that container open to the atmosphere, it will all vanish within probably an hour if it's very volatile. Water's not that volatile, so that's why it takes a long time for all the water to completely evaporate. But it will disappear. It will disappear over time. Okay? So like I said, some molecules evaporate faster. We call them, so molecules that do this, they're generally less polar because they don't have as strong intermolecular forces. It's easier for molecules to leave, and once they start leaving to the gas state, it just becomes this rapid domino effect. So it's for less polar and weaker molecules that have weaker intermolecular forces. So it allows evaporation to be easier and at a lower temperature, and this causes them to have a lower boiling point. So we call these compounds volatile, or substances that have high vapor pressures at room temperature. Okay? So one compound that's like this is diethyl ether, because if you ever work with diethyl ether, once you pour it out, you see vapor forming. So it's a very volatile substance. So in general terms, molecules with vapor pressures higher than that of water are considered volatile, and then those lower are considered non-volatile. Okay, so water's our baseline. So if we look at this table here, again, see these organic compounds? The vapor pressure of diethyl ether is 531. So that's really high. That's almost atmospheric. Now, if we look at something like mercury, very low, and then water at room temperature is 17.5. So see the vast difference there. So bromine would be considered volatile. So is ethanol, acetone, hexane, and then diethyl ether is the most volatile in the list. Okay. So let's go over this example. For example, diethyl ether has a vapor pressure of 531 millimeters of mercury at room temperature, while ethanol has a vapor pressure near 10 times lower, 59. By this comparison, the intermolecular forces in ethanol, what can we say about them? Well, if we have a higher vapor pressure, that means it's easier for the molecules to escape. So that means it has weaker intermolecular forces. So in this case, ethanol has a lower vapor pressure, so its forces must be stronger. Okay? So this makes it more easy or more difficult for ethanol molecules to escape to the gas phase from the liquid. So this makes it more difficult. That's why it has the higher boiling point and lower vapor pressure. It's more difficult to enter the gas phase. So, and thus, from this consequence, we can say ethanol is more polar. More polar than diethyl ether. I was supposed to bold this, not the polar part. Sorry about that. Okay, so it's more polar than diethyl ether, and so it will have a higher boiling point. It takes more energy to go to the gas phase because of the more polar, because of the more stronger intermolecular forces by virtue of being more polar molecule. Okay? All right. So now let's kind of summarize these things here. To summarize, volatile substances have low boiling points. They're easier to go to the gas state, and relatively weak intermolecular forces, easier to go to the gas phase. Between molecules and non-volatile substances have high boiling points and relatively strong intermolecular forces. So that's why water, if you ever try cooking, you wish water would boil faster so you can maybe cook some ramen or some soup, miso soup, or my personal favorite, hot and sour soup. But you have to wait till that water boils, and then once you add stuff in there, you have to wait till it boils again. So it's kind of this annoying process. But there's no way we're going to cook soup with anything other than water, right? So we just have to kind of deal with water's unique properties there. All right. So that's vapor pressure and volatility. two important concepts that we should know. Okay. Next, let's talk about vapor pressure versus boiling point. Okay. All right, so it looks like we'll make it through the last part of chapter 11. So then that'll be the end of chapter 11. Okay, guys? All right, everyone? All right, so vapor pressure versus boiling point. So the temperature at which the vapor pressure equals atmospheric pressure, that's called the boiling point, because once the pressure of your vapor is equal to the atmospheric pressure, there's no pressure differential. So once there's no pressure differential, it's going to, once you reach past the atmospheric pressure, there's no pressure pushing back down onto your system. So once you overpower the system, you're going to evaporate, more gas particles are going to escape into the atmosphere, and that will decrease your pressure of your vapor above solution. And once that happens, more liquid is going to go to the vapor state to replace the gas molecules that went away. So that's why when you see things boil, and that's because you have now enough vapor that equals atmospheric pressure. So now there's nothing pushing against the vapor. The vapor pressure is now not going to be less than the atmospheric pressure. So that's why now the vapor can actually escape get past the pressure of the atmosphere and go into the air. When that happens, that will decrease your vapor pressure above the solution, and when that happens, the system will want to replace that because it's under equilibrium. So when it does that, it's going to keep boiling off the liquid until eventually all your liquid is gone, because now the pressure now will have disappeared because there's no more liquid left. Okay. All right. So the difference between vapor, so what happens here is that once you get to the boiling point, the liquid cannot get any hotter. There's something called a superheated liquid, but we probably won't talk much about that. But as soon as you raise the temperature past the boiling point, you're just heating the gas, and that will just cause a superheated situation. Okay, and then so boiling point basically is any transition from any part of the liquid. So that's why in the boiling point you see bubbles pop up from any part of the liquid. So it means any liquid molecule can now go through the vapor state. Whereas vapor pressure usually only occurs at the surface of the liquid. Okay? So when you reach the boiling point, you pretty much reach the point where all the intermolecular forces between any molecules can be overcome, and then that's why you see bubbles form from any part of the liquid. So it's not accurate to say, okay, when we see gas leaving the liquid, right, or coming off from the liquid, that's the boiling point. Well, that's not true, because you need to see any part where it's basically bubbling from any part of the solution. That's the boiling point. So that's the temperature at which something boils. Okay. All right. So let's wrap up these set of slides here with discussion of the heating and cooling curves for water. All right. So recall back here. So the heating and cooling curves for water. So the heating curve here, we have what we call. So this is an example where we take 75 grams of a sample of ice at 1 atm at negative 20 degrees Celsius, and we heat it at a constant rate. So A to B is called heating solid ice. So how will we determine what temperature we go from there? But in this case, what we do is we take to calculate these energies here, we will from A to B, right? So let's just say we have A to B. from A to B, to calculate the amount of energy it takes to heat this amount of ice, we're going to use our favorite equation, the specific heat equation, mass times specific heat of ice times the change in temperature. Okay? Then eventually we get to point B. B to C is a phase transition. And when we have a phase transition, the amount of heat released or absorbed is equal to delta H. Or in this case, delta H of fusion. So fusion is melting. Okay? And then from C to D, we have another increase in temperature. See the increase in temperature there? We're going to use the same equation here. Q equals mCS of water times delta T. Okay. So in this case, this Q value, it has a specific value. It's negative, it's 6.01 kilojoules per mole. So I'm not sure if we did that in lab, but I think we did something similar. Okay. And then we have vaporizing water. In this case, Q will be equal to, from D to C, or sorry, D to E. Q is going to equal to the delta H of vaporization, vape, and that equals a whopping 40.7 kilojoules per mole. So a very large amount of energy that's released. And that's why it makes evaporating water so difficult, because it takes so much energy to release it. And then once we heat steam from E to F, this will be Q equals mCS delta T. So a popular question we might ask is, okay, how much energy does it take to heat a block of ice that's 75 grams, initially at 1 atm, and negative 23 degrees Celsius to, let's say, 100 degrees Celsius? You would have to go through each of these calculations and add up all the energies to do that. But, you know, I probably will not ask that, but I'm showing you just in case, okay? So you will have to go through these calculations and add the sums to get the total energy required, okay? So see here, as we get to the vaporizing water, you see the temperature doesn't increase, the liquid doesn't increase past 100. What you're heating up in that period after that is gaseous water or steam. All right, so now let's talk about the cooling curve. So cooling curve is basically the opposite. So we go from 200 degrees, we cool back down, go back to water, condensing steam. So in this case, when we look at these curves here are basically the opposite. So this will be delta H of condensation, which equals the negative delta H of vaporization, because remember, it's the backwards process. So this will equal negative 40.7 kilojoules per mole. So it's releasing energy. So that's why you see when you heat up water, it'll release so much energy as it comes back down, back to the liquid state. And then this part from E to F is delta H of freezing. And when we have a freezing, it's going to be the opposite of fusion. So it's an exothermic process. So this is going to be negative 6.02 kilojoules per mole. And then eventually you get to a point where you can supercool water. So eventually, so if water has been supercooled, that means it's pretty much past its past its freezing point, but hasn't frozen. But when something's supercooled, any agitation to that system will cause rapid freezing to occur. So you ever seen those water bottle tricks on like TikTok or YouTube or on all over the internet? It's basically because you form a system where freezing isn't possible, and that's because water is basically, you have a very pure form of water, and there's no like impurities that would cause crystallization to occur. Okay, so very unique circumstances will cause this, but it's pretty cool. It looks like magic, right? So if you've ever seen them, they just freeze, like freezing instantaneously. So it's pretty cool. Okay, so that is it for this this set of lectures. So part 2, learning about the properties of intermolecular forces, then applying them to heating curves, and also talking about vapor pressure, viscosity, capillary action, and surface tension. And I'll see everyone in the next video, where we'll talk about the last part of chapter 11, and that'll be it. That'll be it for this semester. So that'll be all the material, and then next week I will host a review instead of posting lecture videos. Okay, so I'll host a review. I'll host it online, and then in discussion, not this week, but the next week, we'll hold a kind of review session. And this time, I will say, if you can do the review, it'll be the same kind of format on the exam. Okay. So you can trust me on that. I promise. Okay. So I'll see everyone in the next one.